So, back to the question. We have a ball or a hoop on an incline, and the question becomes, if I want to get the acceleration, what am I going to do? Free body dive. So the trick here is we got to be smart about where we draw our the forces. So I clearly have a normal force. Wake up, normal force, right, coming perpendicular to the surface. What other forces are at work here? Gravity. I'm going to draw gravity as coming from the center of the object. Are there any other forces acting on this thing? Yes. Friction. What direction does friction go?
Opposite of motion.
Opposite of motion. So that would be in what direction? Up the incline. Okay.
What if we didn't though?
So in some ways, this makes some sort of sense, because clearly we know that at the bottom, it's not going as fast as it would be if it just slid down the incline, right? So clearly there has to be some sort of force opposing the mg sine theta acceleration. So now that I have my forces, I can write two equations. I can write sum of the forces parallel to the incline, mg sine theta minus force of friction. And that will equal ma. I also, though, need how am I going to determine what the friction is? So, is this kinetic or static friction? Static friction, right? So, we know that static friction is less than or equal to mu static times the normal force, right? So I can't just say mu static mg cosine theta here, right? So I need another equation. So this mass has translational acceleration, but it also has angular acceleration. So I can certainly write I alpha is r cross f. And the f in this equation is going to be force of friction. Does that make sense? So I can write force of friction is I alpha over r. Or remember that alpha is a over r. I can write this as IA over r squared. So now I can come back to this equation right here and rewrite this as ma is mg sine theta minus IA over r squared, or m plus I over r squared times a is mg sine theta, or my acceleration is the forces acting on the system minus the mass and rotational inertia term. And if I go back and compare this to what I got in the previous problem, remember we came up with an expression that looked like V is equal to root GH, and the idea was that that was the energy of a, in this case we used a hoop going down an incline. We can write that, I'm going to go back and write that as V squared is GH, and in this case we could say V squared is equal to G, and the H term just looks like a d sine theta. So H is equal to d sine theta. Is that clear? Are we good on that idea? Going back to where I was, let's plug in for, let's assume it's a hoop. So let's see, hoop, I of a hoop is mr squared. That's going to give me A is mg sine theta over m plus mr squared over r squared. That looks like mg sine theta over 2m. Perfect. The m's are going to cancel out, and I'm left with acceleration is g sine theta over 2. And if I go back to my v squared equation, I would get v squared is v0 squared 2a delta d. Delta d is just h sine theta. Sorry, I messed that up. Delta d is the length of that incline. Acceleration is acceleration is this term right here, and the velocity initial was 0, so we're left with v squared is equal to g sine theta times 2 over 2 times delta d. The 2's cancel out, and I get exactly the same thing I had before. V squared is g sine theta d. V is equal to g d sine theta. So that's a way to look at, another way to look at rolling without slipping. So let's go back to, I guess, this equation here, which is a nice general equation for the acceleration down an incline. Assuming that we have kind of rolling without slipping. Oh, that didn't help me. I don't know where that came from. Edit. Delete.
Try the undo button.
What?
Maybe try the undo button.
Edit. No, that's a good point. Undo typing text.
I tried.
That was something I put in a clipboard from like days ago. Anyway, in general, we found the acceleration was g sine theta divided by m plus I over r squared. We said there was an upward directed friction. Does anybody remember what the tension force looked like? I'm sorry, the friction force looked like? What did I write? Friction is equal to what? Go back in your notes. Somebody look. Force of friction is I A over r squared, correct?
Yes.
Okay. So if I plug this back into here, I get force of friction is I G sine theta over r squared m plus I, correct? And what does friction equal? What is the force of friction defined to be? Force of friction is equal. If I want to know what friction is, friction just in general, friction is equal to what?
Force, force times
Right? So force of friction is mu Fn, which in this case is mu mg cosine theta, going back to stuff we did long ago. Right? So with this, I can write the following. I can write mu mg, and there's a, yeah, we're good. Mu mg sine theta over I plus mr squared. Why did I do that? I can write I g sine theta over r squared m plus I is mu mg cosine theta. The g's are going to cancel out, and I can write an expression for mu. Mu is equal to I tangent theta sine over cosine divided by r squared m plus I. And that's the minimum mu in order for the thing not to slip. Did I leave something out?
Yeah.
There should be an m. Thank you. 1 over m.
Is it also r squared m squared or?
I think r squared m sure is good. Because if I go and the next thing to do would be, let's look at, for a hoop, this would look like mu minimum is m over r squared tangent theta divided 1 over m divided by m r squared plus m r squared. I feel like there's a m that is floating around here that did not get accounted for. Force is equal to I acceleration is g, force is equal to, oh, that's right. That's right. That's right. Think I'm good?
Yeah.
Dimensionally, I'm okay. Oh, because there's an MR, right. Yep, I think I am good. No, I'm,
Oh, you mean I see it on M squared.
yep,
Isn't acceleration mg sine theta over m plus I over r squared? At the very top, you said it was just g sine theta.
acceleration is, there you go.
No, MG sine theta is the force, mass times.
Yes, but I need to have, the M has to be here to cancel out with the M here.
So,
Right,
no, because that's mass times.
it's gonna work out, I promise. I'm now happy.
No, there is an M just. You wrote down the M right there.
There you go. Now I'm good. I was bothered by units. Dimensionally, there was a mistake in there somewhere.
Just dropped an M somewhere.
I dropped what?
Because the one over. Yeah, because we wrote that down earlier. Just like didn't write it down on this slide.
Okay. So that gets rid of that M there. Now I feel comfortable. I feel comfortable because dimensionally everything cancels out. Whoops. That's not what I wanted to do. Perfect. That, and that cancel out, and I'm left with 1/2 tangent theta. And that's half, so here that's half of what we would have had in order for the thing not to slip on an incline. Right? Do we see that? Okay.